Thanks everyone for joining. This presentation is a brief summary of a project that was funded by the Wisconsin Department of Transportation that was completed in 2021. And for this presentation, I'm going to focus on the early age properties of internally cured concrete. As Jason said, everything comes back every 30 years. So we're looking back at internal curing. Not so much on the fundamentals, even though I'm going to talk a little bit about that, but specifically to the state of Wisconsin, they were trying to bring this technology up to the point where contractors and concrete suppliers that are local start to become more comfortable with the concept, with the implications that has on their operations. And sometimes things are not necessarily focused on the technical merits of a project, but also like the communication and the implementation. So that's the cover page of the report. Like I said, it's published in 2021. It's a long report, so obviously not all of the information is going to be covered here, but for anyone who's interested, you can go online and access the report. Is publicly available. So going back to really quick, refreshing our minds about what's internal curing, we're going to try to not provide a source of water that is embedded in the concrete during the mixing process. And that helps with having a more homogeneous distribution of internal moisture that can help with the reaction of the cementitious materials, and that can also have implications on the volumetric changes that concrete materials have, especially on early ages. For several reasons, not only the drying or shrinkage that can occur, but also the effect of self-desiccation and just the creation of hydration products that have a lower volume than the unhydrated materials. So some of the concepts that were touched on the report are, as I mentioned, self-desiccation, when the material by its own reaction is starving itself from water. It can lead to, in some extreme cases, cracking. The lighting isn't great here, but I hope it can be seen in this photograph where the red arrows are pointing a crack that runs horizontally and also vertically. That is attributed to self-desiccation of a cementitious system where the water available was insufficient. We're going to talk a little bit about autogenous shrinkage, the volume changes that the material has from its own reaction processes, and chemical shrinkage, which is basically a microscopic volume reduction just because of what I said earlier, that the hydration products occupy a smaller volume than the unhydrated portion or unhydrated state. And why is that relevant? Well, in construction in pavement and slab on grades, some of the volumetric changes can have undesired effects on volumetric conditions of the material, particularly to warping or curling. Some of that is reversible, meaning that is depending on the moisture condition of the concrete element, and some of that is not going to be gained back if the material has access to external water. And even in many cases, the mixture proportions that are used for like pavements, especially bridge decks, are such that having an external source of water doesn't mean much, because the material is not capable of absorbing enough moisture from the external source and distribute it internally the way it needs to. Part of the project also included a survey of bridges in the Illinois tollway that have used internal curing in their concrete mixtures. There were 6 bridges that were surveyed. Obviously, this is not the focus of the investigation, but in general, the condition of those bridge decks compared to other similar bridge decks in the same tallway system, exposed to the same environmental conditions, same maintenance operations, were found to be in much better shape than bridges that were not built with internal curing. So again, this is not, we're not reinventing the wheel here, it's just reassuring and demonstrating that the technology, when applied or implemented adequately, is actually useful. So the middle portion, or the bulk of the body of the report, was characterizing different sources of internal curing agents, ranging from lightweight fine aggregate, superabsorbent polymers, fibers. We also looked at recycled concrete, and even though it's not going to be discussed here because of time constraints, we started to filter out the materials that were available to Wisconsin for various reasons. Whether, in the case, for example, of recycled concrete, we found that the absorption capacities and the desorption characteristics of different sources were too widely different. Even from the same source, they would change from load to load, which is to the point where it was very unreliable in terms of how it was going to perform. So by a filtering process, we started to screen materials that for example, in Wisconsin, there's a lot of companies that work in the paper industry. So they were very much interested in knowing if any byproducts from the, specifically fibers, from the paper industry have any beneficial performance on concrete. So we looked at that, and ultimately, like I said, we started screening materials based on the absorption and desorption characteristics. We also did morphological studies on the shape of the material. So from left to right, we have a lightweight aggregate, a superabsorbent polymer, and some fibers that were evaluated. And then we started comparing materials, again, on not only their absorption capacity, but also how quickly they lose that moisture when they're in a saturated condition, by putting them in an environment with controlled relative humidity. Because that is also important in selecting the materials for internal curing. You want to make sure that you have enough water, the typical 18%, but how quickly that water is released is relevant, because you don't want that water to be released during the mixing or the placing of the concrete. It has to be released when the system requires that water. So this component is perhaps overlooked, but it's just as important as to how much water the material can hold itself. So in this first slide, I have the lightweight aggregate lightweight fine aggregate, both on the absorption and desorption characteristics. Superabsorbent polymers are very, very capable of absorbing a lot of moisture, and their desorption rate was found to be adequate in most cases. The challenge with the material is in how to add it into the mixture, whether you add it in a dry condition and then have it soak some of the water and maybe compensate for that water in the batching process. If you pre-saturate the superabsorbent polymers before they add it to the concrete mixture, and those have implications on not only how the internal curing process works, but also how the mixture is going to behave. So it's not as straightforward as it can be believed to be. They're very powerful materials. It's just what's the best practice to do that. In this case, these are fibers from different sources. Some are natural, some synthetic. And again, it's just these three slides are basically comparing absorption capacities and the desorption rates based on just the differences in the material. In the case of the fibers, we found that they release the water more quickly than the others. So aside from the shape effects and all of that, we're just documenting the differences of the materials that were found available to the Wisconsin market and which ones would make the most sense for adopting in a specification. Volumetric changes at early age. This is the 1698 test that Jason mentioned, the corrugated tube that was used for evaluating different sources. In this case, I'm just showing a portion of the combinations of materials that were used. In this case, there is 2 lightweight aggregate sources and 2 superabsorbent polymers at different ratios or different dosages. And this slide compares the first day for both on the left-hand side lightweight aggregate and on the right-hand side superabsorbent polymers that were shown in the previous slide. And this is the effect that it has on the early ages from fabrication to setting, and then the change in volume associated for each material. The controls are the same, so those have the same peaks on both charts. This is the same concept, but for after the first day, or at least long term. It all incorporates the results not only from the time 0, but up to 28 days of drying. And the performance is characterized for each material based on not only the dosage that it had, but also the absorption capacities or desorption capacities that these materials have. This is a closed system test, so there's no moisture loss due to drying. It's only the autogenous change from these material hydration processes. In this case, this is, I believe, the 596 results for lightweight aggregate and SAP. You notice that at this point we already started filtering materials, and we're focusing now on lightweight aggregate and SAPs. In this particular case, we use the 596, which is a similar test to 157, but just for mortar. So we're not at the stage where we're implementing these materials in concrete yet. We're still in the characterization phase and working towards the selection of the materials. And finally, just again, a partial view of all the composition or the variables in the study framework and the effect on strength and setting. And to the extent that it was, we were able to measure it, they're all comparable. Nothing was significantly different. Yes, there's going to be a slight reduction in compressive strength by using internal curing. But when we go look at the other components of the study, we'll realize that strength is probably the least of everyone's concerns. There are other things, volumetric performance, durability, that have a much greater impact on what we want structures to look like. So the main portion of the study focuses on 2 different types of concrete mixtures. One, a pavement mixture, and what is called a bridge deck mixtures. These were mixtures that were used in actual Wisconsin DOT projects that were used as reference because they were already approved by the state. There was historical data on compressive strength, on slump, etc. So we have a bulk of or a body of information that we can use to correlate the performance. And again, we have combinations of water-cement ratio, lightweight aggregate sources, and the superabsorbent polymers. For the pavement mixtures, I'm just presenting the results. So everyone who's interested, please go look at the report. It has all the information and a lot of more elaboration on what the results mean. But we looked at the box test and the warping test, just to measure not only the stability of the concrete in a fresh condition, but what are going to be the changes to that material in a quote-unquote more realistic setting where there's differences in moisture availability that are obviously not easily to replicate in a laboratory. And for the bridge deck, we looked again not only on the fresh properties, but also the volumetric changes like the rings, rapid chloride penetrability for chloride or corrosion resistance, resistivity for durability in general, aside from some rheological results on yield stress, how likely these concrete mixtures are for, or how suitable they are for like pumping, aside from other very well-known tests like the air content, the super air meter, etc. These 2 charts show just a comparison of length change in under certain conditions, so a C157 test, and the effect that the materials have not only for internal curing, but also how they compare to each other against the control. On the left-hand side, we have pavement controls and bridge deck controls with a 0.45 water-cement ratio, and on the right-hand side with a 0.36 water-cement ratio. And on the right-hand side, we have the ring test, and we don't present the charts like it was shown before, showing stress. We're focused more on the time to cracking. But we have all that data. It's just that for this presentation, I did not include it as in here. And finally, some of the results of warping. Again, the ultimate objective of the study was to familiarize the department with some of the already established concepts of internal curing, demonstrate that it has been successfully applied by other jurisdictions, and that ultimately it can be a viable way for improving the performance of their concrete infrastructure from the point of controlling volumetric changes and improving the durability and overall service life of the material. There's a component on life cycle analysis and what the effect it has on delayed maintenance, because there is less likely the need of redoing work every 10, 15 years. There's obviously good benefits to the citizens of the state when they have to spend less money in maintaining structures because they perform better. Again, this is a very short summary of what the study is composed of, but again, I want to acknowledge the Department of Transportation, CTL Group Laboratories, where all the work was done. And for those interested, again, please take a look at the report and hope it's useful for you. Thank you.